Hello, our group is Group 2, and we are going to introduce VSEPR theory and linear HECN. My name is Wonjun Cho, and Taeyeon Kwon will uh, participated. Okay, let's move on to content. We are going to predict molecular shape using electron pair dispersion. Let's move on to content.
Uh, We will present first molecular formula and example molecule, second the electron pair and molecular geometry, then fuller analogy and visual, and lastly we present real-world relevances.
Okay, then let's move on to molecular formula and example molecule. There are two questions about this. First one is what is VSEPR theory, and second is what is hydrogen cyanide. It is Prussian acid, and it is example of this theory. Mm, we are going to introduce structure of this molecular formula, and we are going to make easy way to explain this chemical example. Then let's move on to four.
First question, what is VSEPR theory? Uh, VSEPR stands for valence shell electron pair repulsion, a chemical model that predicts the 3D molecular geometry of a molecule based on equation between the electron pair surrounding a third central atom.
Okay,
And
let's move
okay,
on to five. We are introduced about hydrogen cyanide. It is Prussian acid, and I'll introduce about this trait. And okay, carbon is located in the center, so it is the main structure of this acid. And hydrogen and nitrogen are both linked to the carbon, and each element is different, so the bond polarities are not equal. Therefore, this is polar molecule. Let's move on to next sector.
okay. In electron pair and molecular geometry, for HCN there is bonding pairs and lone pair. In bonding pair between hydrogen and carbon makes one bonding pair, and between carbon and N make make three bonding pairs in the triple bond, and total around carbon is two regions of electron density, and lone pairs on nitrogen is one lone pair, and on carbon there is zero lone pair, and on hydrogen there is zero lone pairs too.
Okay, so this structure can make stable form of this acid. And let's move on to molecular geometry. We are going to introduce linear, and this is AX2. This appears when there are two electron density regions around the central atom. These two electron pairs are positions at 180 to 80 angle to minimize repulsion from each other. And the central atom forms a sp hydrogenation, and pi bonds form stably in straight structures. Let's move on to dense Bohr analogy.
denser analogy. Think of the molecule as a tangle. In tango, a man and a woman are dancing together. They are facing each other in a row and balance each other's power. Like this, atoms face each other, but nitrogen's stronger electronegativity leads uh, pulling the electron density, uh, like a male dancer guides the movement. So similar to tango dance, each atom exactly faces each other based on the center, the carbon, because the dipole affects the opposite direction they offset. And nitrogen has a stronger electronegativity than hydrogen. It pulls the other like the male dancer.
Okay, then let's move on to visuals information. In this picture, as you can see, carbon is in the center forms, and it forms one single and one triple bond, this keeping the molecule perfectly straight. Let's move on to real world relevance.
Uh, the, we luckily find real-world relevance. First, polar molecule is one of the examples. Between molecules have strong dipole forces and strong intermolecular attraction leads to a higher boiling point, and HCN is melted well by polar solvents such as water, H2O, and in toxicology relevance, HCN inhibits cellular respiration by binding to iron in cytochrome C oxidase. It stops cells from using oxygen, and in main uses, HCN is primarily utilized in the manufacture of pesticides, insecticides, and pharmaceuticals dyes. So, like this, we investigate the real-world relevance.
Okay, thank you for listening our presentation.